Hi there. In this next video of ours, I'm going to give you some examples of the binomial theorem. I have proven this already in the last video that was such a long video to start out. So I'm going to give you an example or a bunch of examples, and then we're going to end this module in number theory, our module 1, with the corollary of the binomial theorem. So recall our binomial theorem as x plus y quantity raised to n. Summation of n choose r times x n minus raised to n minus r y raised to r from all r from 0 to n. So I'm going to give you a bunch of examples. Shall we have the first? This will be very much a series of examples first. So we have a plus b. Let's have that a plus b or x plus y. Say we raise it to n. So our n is equal to 1. So notice if it is equal raised to 1, so therefore our answer will be a plus b, simply as it is. So if we're going to use this formula, so what we have is the sum of n choose 0 and 1. So we have and 0. So start with that. So for all r, anyways. So our r will be running from 0 to 1. A raised to 1 minus r and y raised to r. So it's very clear that our r will be like running from 0 to 1. So we are expecting two terms here. So if you will really want to see that, so what we have is we're going to turn this into a sum. And then let's start first by 1 choose 0. A raised to 1 minus 0, y raised to 0, that's just equal to 1, plus 1 choose 1, and then we have a raised to 1 minus 1, that's going to become 0, y raised to, oh sorry, should not be y, this should be b. Sorry, my bad. So this must be b, this must be b, and lastly this must be b. Sorry about that. So our r is now, let me just emphasize what happened here. Here we let our r as 0, our first r, and here we let our r as equal to 1. Okay, so by simplification, what we can see is that 1 choose 0 is just 1. It's okay not to write that anymore. A raised to 1, a raised to 1 minus 0 is still a raised to 1. So we have a. Here, this will become 1. This will become 0. That's still 1. B raised to 1 is still b. So thus, this is equal a plus b. Okay, so that's a kind of simple example. Let's try to move on with a plus b squared. So we know this by in our expansion of a binomial. So this is a squared plus 2ab plus b squared. So if we're going to use the binomial theorem, what we can see is, let's start first the formula. So the summation of n, our n is 2, our r is anything ranging from 0 to 2. Okay, and then we have a raised to 2 minus r, b raised to r. Okay, so let's have this. Let's start with r equals 0. So we have 2, choose 0. A 2 minus 0 is still 2. B raised to 0 is 1. So let's not write that anymore. Plus, let's have 2, choose 1. So this will become A 2 minus 1 is just 1. B raised to 1 is just B. Okay, then plus 2, choose 2. That's 1. And then we have a raised to 2 minus 2, that'll become 0, so let's not write that. B raised to 2 is b, yeah, b squared, right? And then what we can see here is that 2 raised to 0 is 1, so we have a squared. 2 choose 1, try to check that, that's the answer is 2, and then we write the variables. Then what we have, 2 choose 2 is still 1, so we have b squared, so pretty much the same here. Okay, pretty much the same in our binomial expansion. and then here. Okay, so let's have one more example, and then we will be making use of one technique, okay, in binomial theorem. So let me use another page for that. So let's try a plus b cubed. Okay, so what is a plus b cubed? Let's say we're not going to use any formula. So we have 3 is n, r is can be any r from 0 to 3. And then what we can say is a raised to 3 minus r, oops, b raised to r. So let's start with 3 raised to 0. 3 raised to 0. So our r is 0. A raised to 3 minus 0. B raised to 0 is still 1. So let's end it there. So let's use 3, choose 1. So that's going to become 3 minus 1. Our r now is 1 here. 3 minus 1 is 2. That's a squared. B raised to 1. So let's write it as a squared b. Then let's move to 3, choose 2. That's our r is equal to 2. A, 3 minus 2 is just a. B raised to 2, that's square. Plus 3, choose 3. So what we can say is a is raised to 3 minus 3, that's 0. So that's only going to be giving us the b left, which is being cubed. Okay, so let's do the combinatorics here, the binomial coefficients. So 3 choose 1 is 1. 3 choose 0 is 1 rather. Again, 3 choose 0 is 1. That's going to be just a cubed. Plus 3 choose 1 is actually, if you're going to apply that, that's going to be 3. If you want the correct answer. So if you want the solving, I'll give it only this example, okay? So what we have is 3 factorial all over 1 factorial times 3 minus 3 minus 1 rather factorial. So what we can see is this becomes 3 factorial all over 2 factorial. Then we can have 3 factorial is 3 times 2 times 1. 2 factorial is just 2 times 1. So just cancel up the 2 times 1, but we will be left with is the 3. Okay, so this is 3. Okay, a squared b plus 3, choose 2. Maybe you can pause the video and try to solve it using this method. Okay, the answer here actually is still 3. Okay, a b squared, and then 3 choose 3 is 1. So we have b cubed. And this is our answer for a plus b quantity cube. Now, if we're going to look at the numbers, the answers, there's such kind of pattern that is happening here. Okay, so here, our first number is a plus b, the first answer, a plus b. If a plus b, quantity a plus b is raised to 1. If a plus b is raised to 2, so we have a squared plus 2ab plus b squared. And then here, we have a cubed plus 3a squared b plus 3ab squared plus b squared. Now, I want you to look at the coefficients. We have 1 and 1 here. Okay, take note of that, 1, 1. Here we can see 1, 2, 1. Again, 1, 2, 1. Here we can see 1, 3, 3, 1. Again, 1, 3, 3, 1. If we're going to write that down in this order, so in the a plus b raised to 1. So the answer is, the coefficients rather are 1 and 1. Okay. If we can have a plus b squared, quantity squared, so what we have is 1, 2, 1. You can see that happening. And then by the a plus b cubed, what we can see is 1, 3, 3, 1. And if I'm going to fill out this one above, this is pretty much our Pascal's triangle. Okay, so this is our Pascal's triangle actually. So if we're going to continue for, of course, this is for a, this is for our a plus b raised to 0. Any number raised to 0 is 1. That's why the answer here is 1. Okay, so if we're going to continue, a plus b cubed, the, what do you call that? The coefficients, a plus b cubed, or rather raised to 4, the coefficients are in the form of 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. If we're going to continue to raise to 5, 1, 5, 10, 10, 5, 1, and then so on. I think you know it already. Okay, so in this example, we're going to make use of a plus b raised to 4, and we're going to use now this time the Pascal's triangle. So let's answer it. A plus b raised to 4. Now, recall our formula. It states that it's all the sum, right? So actually, if I'm going to reread this formula this time, so our n is 4, our r is anything running from 0 to 4, and we have a raised to 4, that's our n minus r, b raised to r. So what is happening here actually is this sum, the summation notation here, okay, the summation notation is simply, okay, it is simply telling us, this is telling us for us to add everything, all the terms, just put a plus sign in between all of them, okay, and then have the Pascal's triangle at hand, and start with a, the first term. It can be x, okay. Start with the first term, and then with that first term, okay, with that first term, you will write the highest exponent with it, and then b will be 0, b raised to 0, that will be 1, okay, and then it will eventually, as r increases, okay, our b also increases, because as you can see, the degree, or shall we say the exponent of the 3 also increases, while the exponent of a decreases. Okay, so I think it's much better if I'm going to explain it by solving. Okay, so looking at the Pascal's triangle, we can see that for the 4, 1, 4, 6, 4, 1. Okay, let's remember that 1, 4, 6, 4, 1. So we know that all the coefficients are 1, 4, 6, 4, 1. Okay, next, we're going to look at the, we're done. So we're done in this part actually, in the coefficients part. What we're going to do now is for the variables, this a and this b. Okay, and then we'll start with a raised to 4, because r is 0 and b is simply 0. 1 rather. B raised to 0 is 1. So we have a raised to 4 plus 4. This a now will be decreased by 1, since r is 1 now. So it's going to be decreased by 1. B will be raised to 1, so that's an existence of the b then. Plus, we have a, this a is cubed, this becomes squared. Now, as you can see, it becomes decreased. It is in decreasing order, while our b increases. Also, the b in opposite is in increasing order. Now we have plus, we have a 3, 4, 3, 2, 1. So it's okay not to write the 1 here. And then b will become raised to 3. And then plus, we have a raised to 0 is just 1, and b raised to 4. And this is our answer for our a plus b quantity raised to 4. Okay, I hope you found that pattern in our binomial theorem. Okay, hopefully. Okay, so how about this one example? Which is this example. So shall we have and then take note of this, please. 2x minus 1 raised to 5. 2x minus 1 raised to 5. Now, for our fifth row, shall we say 1, 2, 3, 4, 5, sixth row rather. fifth if we will not count this up. Okay, so we have 1, 5, 10, 10, 5, 1. Again, 1, 5, 10, 10, 5, 1. So let's have that as in memory. 1, 5, 10, 10, 5, 1. So we can say that this is equal to 1 plus something 5 plus something 10 plus something 10 plus something 5 plus something 1. Okay, let's try to fit that as much as possible. Okay, and what's our A? Now, we're not going to write simply A here because our terms here are already different from A plus B. So our A, which means the first term, is 2x. So this will happen as 1 times, 1 times 2x raised to 5. It's okay not to write the second term anymore because it's simply going to become 0. That's because that r is 0. So any value in the real numbers except 0 will be any raised to 0, that it will be equal to 0. So let's just write it down as that. Next is our 5. Now, our a, our first term 2x will now be raised to, instead of 5, it will be raised to 4. Okay, and then there will be an existence of the b. That is, our b is -1 here. So we have -1 raised to 1. So it's okay not to write that. Let me move this a bit. Okay, let me delete that. Delete this also. I think we will need more space. Okay, 10. Okay, and then 10 raised to, we're going to simply also write 2x. Now raised to 3. Why is it 3, sir? Because 5, 4, 3. It's in decreasing order, and then we have -1. Okay, let's use this one. -1 raised to 2 or squared. Okay, plus. Okay, this will be 10, I think. Okay, 10, I'm sure. 10 times 2x raised to 4 times -1, or rather, not 4, 2 rather. Okay, it's decreasing. Okay, -1 raised to 3. Okay, -1 raised to 3. And then next in our terms is 5. Let me put it here down below. Cannot fit. Plus 5, 2x still raised to 1. That's just 1. And then -1 -1 raised to 4. And then lastly, that's just 1. Okay. Times 2x raised to 0 is still 1, so we'll not write that anymore. And then we have -1. That's our b raised to 5. Okay. What remains to be done is to just simplify this form. So when we simplify, what we'll do is, by number 1, by entity element multiplication, we don't need to write the 1 anymore. So 2x raised to 5. What is 2x raised to 5? So we have 2, 4, 8, 16, 32nd. So that's 32. 32x to the 5th. That's our first term. Plus 2 to the 4th is 16, right? 2, 4, 8, 16. 16 times 5 is going to give us 16 times 5. Well, 16 times 10 is 160 divided by 2. That's going to become 80. 80x to the 4th. And then notice here, we have -1. -1 we'll just change the sign. Instead of plus to become -80, right? Because we have a -1 here in this term. So if there's a -1, this term will have its opposite sign. Next, plus 2 raised to 3 is 8. 8 times 10 is 80 still. X cubed. And then -1 squared is positive, so we don't need to change the sign anymore. Plus 2 2 raised to 2 is 4 times 10, that's 40. 40x squared. And we have a minus raised to 3, -1 raised to 3, so that will become negative. Okay, plus here 5 times 2 is 10x. There's no more raising there. Minus 1 raised to 4 is positive. Okay, so imagine there are two x negative 1 quantity squared. So there are two positive, so it will still become positive. And in the last part, this is negative 1 raised to 5, so that's going to become minus 1. Okay, and this is our answer. Okay, actually, this is our answer. This is the end of our answer. If you have noticed, what we have done is actually making it very, very simple instead of factoring, or rather, writing it very writing it one by one. 2x minus 1 quantity times 2x minus 1 times 2x minus 1 times 2x minus 1. So that's tedious to do. Write it times 5 times. So, okay. So using this binomial theorem will really help how we do the expansion of a binomial. Okay. In algebra. That's why I said in my college algebra course, the binomials have a special have a special role in mathematics, such as this one in the binomial theorem. Okay, so that's it for all my examples in binomial theorem. So we have our first example as a raised to 1. It's just equal to a plus b. We have our example in a plus b quantity squared. We have our example in a plus b cubed. And then a plus b raised to 4 is over here. And a plus b. And in all a, raised to 5. So what we're doing here is actually making use of the Pascal's triangle and answering the binomial coefficient. Okay. Now, before we end, I'm going to introduce a very short corollary. Okay. A corollary, just recall, that a corollary in mathematics is a result. Okay. It's a result corollary. Let me write this correctly. So a corollary, okay, is a result that follows from a previous theorem. So from our binomial theorem, um, we will be using this as one corollary. So the theorem can be used to establish several interesting identities, shall we say, involving binomial coefficients. The following corollary shows that the sum the sum of n choose r running from 0 to n is equal to 2 raised to n. Equal to 2 raised to n. So the sum of the binomial coefficients is 2 raised to n. So you want to bet? Okay, the sum of the binomial coefficients is 2 raised to n. So let's have this as an example. Okay, so 2 raised to n. So 2 raised to 1. The sum is 2. Clearly enough, 1 plus 1 is 2. Next, let's try the second example. So the sum of the coefficients is 2 raised to n. So we have 2 raised to 2. The answer is 4. So pretty enough, 1 plus 2 plus 3, that's 4. The sum here is 2 raised to 3. This is equal to 8, right? So 1 plus 3, 4, plus 3, 7, plus 1, 8. Okay, pretty much. For the a raised to 4, 2 raised to 4 is equal to 16. Okay, 1 plus 4, 5, plus 6, 11, plus 4, 15, plus 1, 16. And then this will be 30, 32 for the fifth. Okay, so that's it. If it's going to be a plus b only, if it's going to be a plus b. Okay, so if you want to check that, we can go back in the previous slide. So here, 1 plus 5 is 6, plus 10, 16, plus 10, 26, plus 5, 31, plus 1, that's going to be 32. So it follows that the binomial theorem, that the binomial coefficients is the expansion of x plus y raised to n in the various rows in the Pascal's triangle. This is very clear, of course. And how can we give a sum of a proof of this? So for the proof, if you want the proof, I'll just give you a direct proof. So we will let x equals 1 and y is also equal to 1 from the binomial theorem. So if we do that in the binomial theorem, so recall our binomial theorem as x plus y raised to n is equal to the summation of n choose r x raised to n minus r y raised to r from all r 0 to n. Okay, so let's let all the x's and the y's to be equal to 1. So clearly here 1 plus 1 is 2. This is 2n. We cannot do anything with the summation notation, so I think we just need to copy it, though I'll try to make it fit. Okay, that's challenging. Okay, so we have r equals 0. Anyways, I'm going to write it in this way. R equals 0 until n. Okay, that's also one LaTeX way of writing that. Of n choose r. So our x and y are all 1. So 1 raised to any number at all, okay, which are all integers. So or I mean positive integers, that's going to be still 1. 1 raised to 100 is still 1, right? Multiply 100 times, so that's still 1. So yeah, so that's the end of proof, I think, right? This is already the corollary, correct? This one. Okay, so therefore this is the end of proof and we have ended it. Okay, so that's it for this video. I hope you learned something, and I hope that giving you examples of the binomial theorem makes the binomial theorem now useful in expanding binomials in the nth degree. And also this corollary will be giving you the bird's eye view of what will be the sum of the coefficients. So thank you very much for watching. See you in the next video. Don't forget to like and subscribe, and yeah, see you next time. Bye.